All right, this video is just a continuation from the first part. We're using the shell method to find the volume of solids revolved around the y-axis. In the last couple examples, we just had a single curve that was revolved around the y-axis. So in this example, we're going to see what happens when we have two intersecting curves or two intersecting graphs revolved around the y-axis. And I'm going to show you how we could use either the shell method or the washer method. So we'll compare both methods. Sometimes the information given allows you to have your choice as to which method you prefer. Other times, one of these methods might be more difficult than the other. It's just always based on the example or the problem given. So this one, we have the graph y equals x. That would be our linear function right here. And the graph y equals x squared, which would be our parabola down here. So those two graphs are going to intersect. We can find the intersection points by setting them equal to each other. Or we can visualize the two graphs. We can see the intersection happening for x values of 0 and 1. For the washer method, because I'm revolving around the y-axis, I want my equations in terms of y. So if we solve this equation for y, we're just really flipping it. It's x equals y. But if I solve this equation in terms of y, it's going to be, I'm going to square root both sides and get x equals the square root of x. So this curve right here is actually x equals the square root of y, or y equals x squared. It's represented by both. All right, so let's figure out how we can use the shell method. The shell method is saying that we need to know what our shell radius is and our shell height. And then we can use this formula and we can use our equations in terms of x. So that's one nice thing about the shell method is even though we're revolving around the y-axis, we're allowed to do everything in terms of x. Whereas the washer method, if I want to revolve around the y-axis, I need my equations in terms of y. So that's another thing that may make the washer method a little tricky. But once you get the hang of it, maybe both of these methods are equally easy. All right, so the shell radius. The shell radius is determined by the x value that we're using. So if our shell is this wide, well, that would be the x value would be our radius, or that distance right there. Whereas if our shell was this wide, well, then the radius of that shell would be this x value. So the shell radius is our x value. So I'm going to substitute x right there. The shell height is the tricky thing when we have intersecting graphs, at least at first. Our shell height can't be any higher than the area that we are trying to fit our shell into. So it's got to fit in between these two graphs. Well, the shell height is going to be the height difference between our two functions. So this output and this output, what's the difference between those 2 points? That would be that shell height. And it's going to be different wherever we are on our graph or wherever we're at in the area of our in between our two curves. So if I want to find the distance between two vertical points, I could take my top point and subtract my bottom point, and that would be the distance between the 2 points. Well, if this is given to me by the output of x, and this point is given to me by the output of x squared, I could do x minus x squared to get the shell height. From there, we could distribute our x and simplify this. So x times x is x squared, x times negative x squared is negative x cubed. Now we can integrate, and we'll integrate from 0 to 1, being the x intersection points. We're going to find our antiderivative. So the antiderivative of x cubed is, or x squared is x cubed over 3. The antiderivative of negative x cubed is negative x to the 4th over 4. And we're going to evaluate that antiderivative at 1 minus evaluating the antiderivative at 0. Plugging in a 1, we get 1/3 minus 1/4. Plugging in a 0 just gives us 0, so if we subtract 0, we can ignore that. So let's just focus on 1/3 minus 1/4. Get a common denominator if you want to do it in fractions. So 4/12 minus 3/12. It's hard to say. And we get 1/12. If I multiply that by 2 pi, I get pi over 6. Let's see how we can use the washer method to get the exact same answer. So again, in order to use the washer method rotated around the y-axis, we need our equations in terms of y. So our inner function is what we're going to subtract from our outer function when we use the washer method. The outer curve is now the square root of y. So I'm going to square the square root of y. My inner curve is x equals y, or just y here. So if I square that, I get y squared. And if I square the square root of y, I just get y. All I need to do now is find the antiderivative and evaluate it. Oh, the limits of integration. They're not the same, even though it says 0 and 1 here. This was in terms of x, so I was talking about these limits on my interval from 0 to 1 on the x-axis. However, with the washer method, everything was in terms of y, so we're looking for the intersection points, the y values of the intersection points. Those just happen to be the exact same in this example, not always the same in every case though. So we can find our y value intersections by setting the y equations equal to each other, or the equations in terms of y equal to each other. It just happens to be the exact same values. All right, back to evaluating. We find the antiderivative. Antiderivative of y is y squared over 2. Antiderivative of y cubed over is y squared is y cubed over 3. Wow. I'm going to get with it here in a minute. Here's our antiderivative. We're going to evaluate that at 1. So we get 1/2 minus 1/3. We're going to evaluate it at 0. And we just get minus 0. We don't care about that. So we're just doing this subtraction here. We can get a common denominator to do it in fraction form and get 3/6 minus 2/6, which is 1/6. And finally multiply it by that pi that was waiting for us the whole time, and we get pi over 6, the exact same volume. So it didn't matter which method we used, as long as we used them correctly. The shell method is nice because we can find the volume of things rotated around the y-axis in terms of x. So if we're given equations in terms of x, we don't have to resolve them in terms of y in order to find the volume rotated around the y-axis. However, we can use the washer method if we are comfortable enough doing that. Make sure that everything is in terms of y, including your limits of integration. And hopefully, regardless of whatever method you use, you should get the exact same volume.